The Big Bang Theory is a broadly accepted model for the origin and evolution of our universe. It postulates that 14 billion years ago, the portion of the universe we can see today was only a few millimeters, if that, across. It has since expanded from this hot, dense state into the vast and much cooler cosmos we currently inhabit. We can see remnants of this hot, dense matter as the now very cold cosmic microwave background radiation, which still pervades in the universe and is visible to microwave detectors as a uniform glow across the entire sky. The Wilkinson Microwave Anisotropy Probe, better known as WMAP, was a NASA Explorer mission. It had produced a wealth of precise and accurate cosmological information. WMAP produced the first full-sky map of the microwave sky with a resolution of under a degree, and that's about the angular size of the moon. The patterns in the map result from well-understood physical processes that happened when the universe was young. By matching the patterns in the map to the physics we know, WMAP was able to produce a convincing consensus on the contents of the universe. The cosmic microwave background, or CMB radiation, is the light left over from the Big Bang, shifted to microwave wavelengths due to the expansion of the universe. The whole universe is bathed in this afterglow light. This is the oldest light in the universe and has been traveling across the universe for about 14 billion years. The light patterns across the sky encode a wealth of details about the history, shape, content, and perhaps the ultimate fate of the universe. The Big Bang Theory rests on two theoretical pillars. The first key idea dates to 1916, when Einstein developed his general theory of relativity, which he proposed as a new theory of gravity. His theory generalizes Isaac Newton's original theory of gravity, in that it is supposed to be valid for bodies in motion as well as bodies at rest. Newton's gravity is only valid for bodies at rest or moving very slowly compared to the speed of light. A key concept of general relativity is that gravity is no longer described by a gravitational field, but rather it is supposed to be a distortion of space and time itself. Physicist John Wheeler put it well when he said, "Matter tells space how to curve, and space tells matter how to move." Originally, the theory was able to account for peculiarities in the orbit of Mercury and the bending of light by the Sun, both unexplained in Isaac Newton's theory of gravity. In recent years, the theory has passed a series of other rigorous tests. After the introduction of general relativity, a number of scientists, including Einstein, trying to apply the new gravitational dynamics to the universe as a whole. At the time, this required an assumption about how the matter in the universe was distributed. The simplest assumption to make is that if you viewed the contents of the universe with sufficiently poor vision, it would appear roughly the same everywhere in every direction. That is, the matter in the universe is homogeneous and isotropic when averaged over very large scales. This is called the cosmological principle. This assumption is being tested continuously as we actually observe the distribution of galaxies on ever larger scales. The Big Bang model is not complete. For example, it does not explain why the universe is so uniform on the very largest scales, or indeed why it is so non-uniform on smaller scales. In other words, how stars and galaxies came to be. The Big Bang model is based on the cosmological principle, which assumes that matter in the universe is uniformly distributed on all scales, large and small. This is a very useful approximation that allows one to develop the basic Big Bang scenario, but a more complete understanding of our universe requires going beyond the cosmological principle. Many cosmologists suspect that inflation theory, an extension of the Big Bang theory, may provide the framework for explaining the large-scale uniformity of our universe and the origin of structure within it.